In today's deep dive, we explore the intricate concept of the multiverse, a theoretical framework that challenges our very notion of a singular, linear reality. This discussion examines advanced models in which not only multiple universes but infinite variations of every entity, including infinite versions of you, might exist. The interplay of quantum mechanics and cosmology has given rise to models that suggest an inexhaustible landscape of alternate realities, each governed by its own set of physical laws, constants, and boundary conditions. We will rigorously examine speculative constructs such as the level, 2, 3, and 4 multiverses, as defined by leading cosmologists, alongside the mathematical structures supporting these ideas. Concepts like eternal inflation, the stochastic nature of cosmic expansion, and the complex vacuum landscape in string theory add layers of complexity to our conversation, challenging even the most seasoned experts to integrate empirical data with theoretical predictions. Our journey combines technical rigor with clear, relaxed language, ensuring that advanced discussions are elucidated precisely yet accessibly. Detailed quantitative analyses based on experimental physics, high-precision cosmological measurements, and state-of-the-art computational simulations are woven into the narrative. We will consider equations underpinning quantum decoherence, statistical mechanics supporting inflationary models, and probabilistic interpretations that suggest every quantum event spawns alternate outcomes. With data derived from satellite missions like Planck and particle interactions observed at the Large Hadron Collider, we aim to connect hard science with profound theoretical implications. This exploration is not only a review of historical scientific evolution, but also a presentation of cutting-edge research drawing on mathematical clarity and rigorous numerical analysis. Prepare to engage with models that seamlessly merge high-level mathematics, advanced simulations, and philosophical inquiry into what an infinite series of realities truly means. The idea of multiple universes has roots reaching deep into history. Early philosophical frameworks, from ancient Greek thought through medieval mysticism, entertained the possibility of parallel realms and alternate existences. Philosophers like Anaximander posited that the cosmos might extend far beyond the immediately observable, while later mystics pondered an intertwined tapestry of worlds governed by different parameters. During the Enlightenment, discussions about infinity, space, and the potential for innumerable worlds were advanced, setting a philosophical stage that would later influence scientific inquiry. The emergence of modern science transformed these early musings into mathematically robust frameworks. In the early 20th century, quantum mechanics introduced phenomena such as superposition and entanglement, which invited technical speculation about multiple outcomes for every quantum event. These ideas culminated in Hugh Everett III's many worlds interpretation, where the universe undergoes continuous branching with every quantum measurement. Meanwhile, Einstein's general relativity reshaped our understanding of spacetime, suggesting that under certain conditions, entire universes might emerge independently from varying initial parameters. Cosmological models further cemented the plausibility of a multiverse. The Big Bang theory, augmented by the concept of cosmic inflation, posited that our observable universe might be merely one bubble in an eternally inflating, frothy cosmos. Pioneering work by Alan Guth and Andre Linde introduced mathematical models in which non-uniform cessation of inflation produces separated cosmic regions with distinct physical conditions. Detailed numerical simulations in high-energy physics and cosmology have since supported this speculative framework, providing statistical evidence that multiple, causally disconnected realms can naturally arise from the same fundamental laws. Historical perspectives remind us that the multiverse has evolved from philosophical speculation into a topic where technical rigor and quantitative detail are paramount, setting the stage for modern debates enriched by precise, fact-driven analysis. At the forefront of modern theoretical physics lies the scientific framework underpinning the multiverse hypothesis. Central to this discussion is quantum mechanics, which fundamentally challenges the classic notion of a single, linear reality. One of the earliest proposals was Hugh Everett III's many worlds interpretation, circa 1957, which posits that every quantum measurement results in a branching of the cosmos. In this framework, each possible outcome is realized in its own distinct branch, thereby suggesting an effectively infinite set of universes where every quantum possibility is actualized. Advanced experiments in quantum computing and quantum entanglement have illustrated phenomena, such as coherence and decoherence, that demand rigorous mathematical modeling to describe the splitting of outcomes. These developments provide a quantitative basis whereby minute variations at the quantum level could be amplified into macro realities. Cosmological theories contribute similar depth to this investigation. The modern theory of cosmic inflation, introduced by Alan Guth and refined by André Linde, predicts that the rapid exponential expansion of space may not have ended uniformly. Instead, a stochastic inflationary model implies that isolated pockets of space cease their inflationary phase at different intervals, forming a vast multitude of bubble universes. These bubbles are hypothesized to possess distinct physical parameters, with differences attributed to local symmetry breaking and vacuum selection effects. Cutting-edge numerical simulations, relying on Monte Carlo methods and lattice-based computations, have demonstrated that even minute fluctuations in the inflaton field can lead to divergent outcomes, producing a statistically infinite variety of universes. String theory introduces an additional layer of sophistication. At its core, string theory contends that the fundamental building blocks of reality are one-dimensional strings, the vibrational modes of which manifest as the different elementary particles. The mathematical formulation of string theory necessitates additional spatial dimensions that are compactified on complex shapes such as Calabi-Yau manifolds. Detailed calculations reveal an enormous degeneracy of possible vacuum states, with estimates sometimes reaching on the order of 10^500 solutions. This vast landscape of vacua implies that each solution corresponds to a unique universe endowed with its own set of physical constants and laws. Such a panorama is not only mathematically intriguing, but also quantitatively challenging, as researchers strive to determine probabilities for our observed laws within this expansive framework. Empirical evidence, though indirect, continues to bolster the multiverse discussion. Precision measurements of the cosmic microwave background radiation by satellites like Planck have identified subtle anomalies, some of which are interpreted as potential imprints of collisions between our universe and adjacent bubble universes. In parallel, high-energy experiments at facilities such as the Large Hadron Collider probe particle interactions that might hint at higher dimensional effects predicted by string theory. Beyond the rigorous mathematical models and precise experimental data, the multiverse hypothesis raises profound philosophical and existential questions. One of the most intriguing issues is the challenge it poses to our classical concept of identity. If every quantum event spawns alternative realities, then the notion of a continuous singular self becomes complicated. In a multiverse, infinite versions of an individual could exist, each diverging based on minute differences in decisions or random events. This interpretation forces us to confront the idea that identity might not be fixed but rather a fluid, probabilistic phenomenon. Quantitative models in probability theory and Bayesian statistics provide frameworks to explore these variations, serving as a bridge between abstract theoretical notions and our understanding of personal identity. The interplay between free will and determinism also acquires new dimensions within the multiverse context. In scenarios where all conceivable outcomes are realized, traditional concepts of causality become less definitive. Advanced statistical models suggest that every choice might branch into a cascade of potential realities. This idea resonates with age-old philosophical debates, predestination versus libertarian free will, where modern mathematical formulations now offer precise, number-driven insights. By applying rigorous probabilistic analysis, one can argue that the very fabric of decision-making is infused with uncertainty, and consequences are as much a matter of chance as they are of deterministic sequences. Moreover, the recognition that the laws of physics, life's emergence, and even fundamental constants might vary across different universes compels us to reconsider the meaning of existence. Does the prospect of infinite versions of reality diminish the uniqueness of our own, or does it instead highlight the significance of every individual configuration as a singular phenomenon amidst a cosmic ensemble? Popular culture has long embraced the concept of the multiverse, incorporating it into films, television series, comics, and literature, with both creative flair and technical nuance. Science fiction narratives draw on advanced theories, such as quantum tunneling, temporal loops, and multidimensional spaces, to present alternate realities that, while speculative, are underpinned by scientific concepts. These visual and narrative representations often integrate complex scientific terminology and advanced mathematical ideas, subtly referencing the rigorous research conducted in modern physics and cosmology. Blockbuster films and acclaimed series frequently depict parallel universes where characters navigate different life outcomes. Their portrayals of cosmic events, inspired by phenomena like bubble universe collisions and quantum decoherence, resonate with contemporary academic discourse. In these narratives, technical details such as fluctuating space-time metrics and shifts in vacuum energy are hinted at, connecting creative storytelling with research on inflationary dynamics and string theory. Such depictions encourage viewers to appreciate high-level theory while engaging with accessible, visually rich narratives. Similarly, the world of comics provides fertile ground for multiverse narratives. Iconic heroes traverse diverse universes, encountering alternative versions of themselves and facing moral dilemmas born from divergent historical outcomes. In closing, our exploration of the multiverse has traversed a wide spectrum, from rigorous mathematical models and precise experimental data to profound philosophical inquiry and cultural reinterpretation. The detailed analysis of quantum mechanics, inflationary cosmology, and string theory has provided a technical scaffold supporting the bold claim that our universe might be just one branch among an infinite arboreal reality. The convergence of empirical observations, ranging from cosmic microwave background anomalies to high-energy particle experiments, with advanced computational simulations, paints a picture of a complex, layered cosmos. Looking forward, ongoing research in high-energy physics, cosmology, and quantum computing promises to refine our understanding of multiverse dynamics. As experiments evolve, whether through further analysis of astrophysical data or through breakthroughs at particle colliders, the precision of our models will undoubtedly improve. Sophisticated mathematical tools such as topology, advanced statistical mechanics, and state-of-the-art computational methods will continue to shape our interpretation of multiverse phenomena, bridging theory with observation. The potential detection of subtle signatures, like imprints of quantum events or minute fluctuations in background radiation, could provide decisive evidence for collisions between bubble universes or higher dimensional effects predicted by string theory. These discoveries may revolutionize our grasp of fundamental physics, offering a more complete, quantitatively robust picture of reality.